to the cloud, and I will post the recording after we're done. All right. So hopefully you found the Zoom midterm review packet, which is on the same page with the link to this webinar. And that page is also where I will be posting the recording afterwards here. So how many of us are there? 44. Well, that's pretty good. That's like 25% of the class. So that's good. So we covered chapter 5 pretty well. I want to circle back to chapter 4, organic compounds, so specifically naming them given different types of structures. So we have like a condensed structure here, we have line structure or skeletal structures. So I want to start on chapter 4. Let's work backwards. So we already did some naming already. And please use the chat feature if you need to get my attention or have a question or something or want to suggest a problem. Since none of you can unmute yourself, really all I have is the chat. All right, so let's start with chapter 4, but starting at the end. So this is question 6. So we're looking at the consequences of, building molecules and how do those, substituents exist in three-dimensional space. So we talk about a lot of different isomers, different kinds. So we'll go into the details of those as we work backwards through chapter 4. All right, so question 6 here says, which of the following can exist as a pair of cis and trans isomers? So this is a type of geometric isomer. All right, geometric isomer, or it also falls under this stereoisomer. Isomer. So the whole deal and kind of point to these types of isomers is that their substituents exist differently in 3 dimensions. And so these, when you're looking at a pair of cis and trans isomers, they are unique molecules that you can't flip them or twist them to make them look the same, that they are they're completely different. So I have a strategy for identifying cis and trans isomers. So typically when we think cis and trans, cis means that the substituents are together on the same side, while trans, they're opposite to one another. So let's inspect these different structures, and you might have noticed that this question is a repeat from the in-class. I think this question was in the in-class one, and I think it was on a practice midterm because this is a tricky question. So let's inspect these different molecules to see if they exist as cis and trans isomers. Oh, and I should point out, with cis and trans, they can either our kind of base molecule that we look at, whether the substituents are on the same side or on opposite sides. We look at either alkenes, so that's what we see in this case, so any double bonds and the substituents across those double bonds, or we can look at rings, because once you have a molecule in a ring, that you can also see cis and trans isomerization. All right, so let's look at this molecule. So what we want to focus on are the 4 groups that are around the carbon-carbon double bond. So I like to highlight the ones that are the same and inspect them and see, okay, if I change not the connectivity, but change, flip 2 of the bonds, 2 of these types of bonds from one another, do we make a new unique molecule? So we have 3 methyl groups and a chlorine group on this molecule. So where geometric isomerization comes into play is, let's not change the connectivity, but let's just change the place of 2 of the groups on one of the carbons and see if that's a new unique molecule. So you have plenty of time on this exam, so it really helps to just draw out what that other structure would look like instead of just thinking about it in your mind. So let's draw that. If we flip those 2 substituents off of this carbon, it would look something like this. We have a carbon-carbon double bond, we have a CH3, all right, and then now the CH3 is down here, and then the other chlorine is up there. All right, so that's the other, if we flipped it. So note here that if you look at each carbon, this carbon still has a chlorine and a CH3 attached to it. So we did not change the connectivity of that carbon. All we did is changed where these groups exist in 3 dimensions, because this double bond prevents us from twisting the molecule like you would in a single bonded carbon-carbon. And then if we look at this carbon center, see how the connectivity is exactly the same. We have a CH3 and a CH3. All right, so I'll highlight those CH3 groups to kind of identify where those are, and then highlight chlorine is different there. So if you look at this too fast, you might say, oh yeah, that's a different molecule. But remember, this molecule's flat. So if I just flipped like a pancake, like flipped this second molecule that I drew, it's actually the same molecule. That these two molecules, they're the same. I just flipped them. I flipped it upside down like a pancake. All right, so those are the same molecules. So these cannot exist as cis and trans isomers. They can't. Because once you try to change the stereochemistry around these carbon-carbon centers, it's still the same molecule. All right, so oftentimes what we're looking for are 2 unique substituents across the double-double bond, like in number 2. In number 2, I see that there's 2 chlorines on this molecule. All right, and then we have some other groups over here, but it doesn't matter. So I'm going to use the same strategy here. I will switch places of 2 of the stereochemistry on one of the carbons, flip their places, and note that I'm just flipping just one of them. And you can choose this one too. It doesn't matter. Just pick one of them, and I'll redraw that molecule. So C, double bond C. Now my chlorine is up here. CH3 is down here. All right, Cl, Br, those ones didn't change. So now if we look and see where those chlorine atoms are, these are trans to one another, right? These are trans from one another. They're across the double bond from one another. While this one, the one that we were given, is cis. So these are unique molecules that there's no flipping or rotating that you can do to make these 2 molecules look exactly the same. So 2 is a molecule that can undergo have a cis and trans isomer. So really the strategy here is to try to make the other cis or trans isomer and see if that is a unique molecule. All right, so 2 is an answer, 1 was not. Let's look at 3, because this one can be tricky too. Because when we look at, this molecule, these 2 chlorines are cis to one another, meaning that these chlorines that are bonded to different carbons across the double bond, they are cis to one another. So oftentimes students will think when we have 2 chlorines together on one carbon atom that this is cis. This is not cis. All right, because these chlorines are on the same carbon atom, that we actually need the same molecule on different carbon atoms. So I'm going to highlight these 2 chlorines here and do the same exact thing and try to see if I can't make a cis or trans isomer. So I'll just flip these 2 substituents around that carbon, the other carbon atom. All right, so note here, I'm not switching these 2 groups, because then I would be changing the connectivity of the actual molecule. So let's redraw this. So carbon, CH3, hydrogen, chlorine, chlorine. And so I'll highlight those chlorines. And note here that this is actually the exact same molecule. I just flipped it like hot dog style. And it's the same exact molecule. So 3 is not a cis or trans isomer either. All right, so the question here, there's a question on the practice exam like this. It had an H. Okay, so okay, so we have carbon, you said it had H and CH3 on the top and Br and H on the bottom. And it can exist as a cis and trans isomer. So this example right here is actually the exact same as number 2. It's just instead of chlorines, it's hydrogens. So it's the exact same question. So in this example, I'm going to highlight the 2 substituents that are the same. So hydrogen and hydrogen. So this would be a trans isomer because those hydrogens are opposite from one another. But if we do the same idea. If we flip 2 of the groups off of 1 carbon, so we're not changing the connectivity, all we're doing is changing the stereochemistry, and then we redraw that. All right, so we have an H and the other 2 kind of stay the same here. All right, so CH3, this is a unique molecule. This would be the cis isomer because those hydrogens are together on the same side. Okay. Yeah, so yeah, hydrogen's the same. Okay, Tanya said, why the first one won't be a cis isomer again? Yes. Okay, so the reasoning, well, one, if you try to name this as a cis or trans isomer, the question is, what are you looking at? So there's 3 groups that are all the same. These 2 groups are cis to one another, but these 2 groups are trans to one another. So is it cis or is it trans? I don't know. So I think how I approach this question is I tried to make in all of these examples, I took one of the carbons and I switched the places of the 2 groups that are on one of the carbons. And I compared the 2 molecules that I have and thought, are they the same molecule or are they different? So I decided to switch this group and then this chlorine. So I switched those one. And then once I switched them, that chlorine atom is now up here. And now if I kind of zoom out and compare those 2 molecules, at first glance, you might say, oh yeah, those are different molecules, but they're actually not. If you flip this molecule just upside down, it is actually, they're the same molecule, or you could just rotate it and it's the same molecule. So that first one is, they're the same molecule. Really, you need to have at least 2 groups that are the same to have cis or trans isomers, and they have to be on different carbons. So that's kind of the big idea there. So our answer here is just 2 only. Okay, there we go. All right, so there are cis and trans isomers. So let's go look at some more isomers here. All right, so we talked about cis and trans isomers, which are geometric isomers. There are also other types of isomers that we can have too, actually right here, kind of list them all. We have structural isomers, conformational isomers, and then we have our stereoisomers within there. So the big idea with isomers, all isomers share the same chemical formula. There's the same number of atoms in each of those compounds. Where we can differ is structural isomers have different connectivity, for example. So in these examples, all of these things, even the flipped ones that I make, they have the exact same connectivity. They differ in 3-dimensional space. That's why they're stereoisomers. Structural isomers have the same formula, but the connectivity is different. So for example, if I have butane here, 4 carbons, it could be in a straight chain, but I could also have 2-methyl propane. Both of these molecules actually have the exact same chemical formula. They're C4H10, I think, all right, both of them, but the connectivity is way, way different. We have a straight chain here. In this guy, we have a carbon that's attached to 3 other carbons. These are 2 completely different molecules. They have different names to them. So they are structural isomers because you're taking Lego pieces and building them, you're building different things, right? It's like I give to like you and your friend the same Lego pieces, but one of you builds a boat and the other builds a house. That's a structural isomer, but you start with the same pieces. So in this question, it's just a true or false question. These 2 molecules are structural isomers. So we want to see is their connectivity the same? Or another way you can think of it is you can name them and see if they have the same name, then they can't be structural isomers. Structural isomers have to have different names. So if I kind of inspect this and look for the longest chain, I see that there's a 5 chain carbon there, and then there's a 2 carbon substituent right there. So if I look at the other molecule, if you inspect very carefully, there's a 5-membered chain, the parent chain right there, and a substituent, a 2 carbon substituent there. So I can name it, but I see that these are actually the exact same molecule. They are. I literally copied this molecule a second time and then rotated it. So these are actually conformational isomers. They are actually the same molecule, conformational, I think I spelled that wrong, isomers. They are not They are not structural isomers. So this is false. These are the same exact molecule. I just rotated it. So structural isomer, again, it's the pieces, the building blocks, they're put together differently, but these are the same molecule. And I got that by rotating the bonds differently. Also, you could think, you might see that the parent chain is right here. All right, that's 5 carbons and then a 2 carbon substituent there. It's the same exact molecule. So these are conformational isomers, not structural isomers. All right, we got that? We got that. Keep going. Okay, so let's look at these two. Let's see if these compounds are related at all. So we're kind of still thinking about isomers now. And remember, isomers always mean any isomer always shares the same chemical formula, shares same formula. So if you are comparing two molecules that don't have the same chemical formula, then they're not isomers at all. So it would be C. They are neither structural nor conformational isomers if they don't share the same chemical formula. But in this case, if we really inspect and take our time and make sure that both of these molecules have the same chemical formula, why don't we get the chemical formula for this compound? Because I think that's good practice with line structures like this, or skeleton structures, because skeleton structures don't have the hydrogens in them. And so you kind of have to figure out how many there are. So my idea here with skeletal structures is identify where all the carbons are. So there are all my carbons, and then there's one as a substituent right there. So there is 1, 2, 3, 4, 5, 6, 7 carbons, C7. There's an oxygen there. And then I need to figure out how many hydrogens are on all of the carbons. So I'll just kind of draw little tick marks. So remember, carbon always forms 4 bonds. So this carbon on the end has 3 hydrogens attached to it. Then this carbon has 1 hydrogen attached to it because it already is bonded to 3 other carbons. This hydrogen has 2. Actually, all 4 of these have 2 carbons along the ring. All right, then if we look at this carbon, that's the carbonyl carbon, does not have any hydrogens because there is already 1, 2, 3, 4, 2 bonds coming from the double bond. That carbonyl carbon has no hydrogens, and then that's it. So there's a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 carbons. So H12. So let's look at the other compound as well. Hopefully you can see that these are isomers because you have the exact same chemical formula. So there's 7 carbons. Very good. There's an oxygen from that ketone group there. And then if we draw the hydrogens in 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is C7H12O as well. So these are isomers because they have the exact same chemical formula. But now we need to go into a little bit more detail and think, okay, what kind of isomers are they? So these molecules, so see that we have this ketone group, kind of at 2 o'clock here. On this first molecule, we have a methyl group, one of the substituents coming off the 12 o'clock position. But in this one, it's on a different carbon. So let me just number the carbon so it's a little bit easier. If we call the ketone carbon 1, on this first molecule, that methyl group is on carbon 2, but on the second molecule, that methyl group is on carbon 3. So if we named this, though we don't have to figure out this question, it would be like this molecule would be a 1,2 substituent cyclohexane, while this one would be 1,3. So there are different names because the connectivity is different. So these 2 molecules are actually structural isomers. They are made of the same Lego pieces. They are just connected differently because we have a methyl group connected here in this molecule, but it's connected somewhere else in this molecule. So these 2, you might right off the bat just think like, oh, those are different molecules. They're nothing. They're unrelated, but they actually are related. They are similar molecules. They have the same chemical formula, but their structure is just a tiny bit different. And that can give us a little bit of different properties when we inspect or observe chemical properties in substances. All right, so structural isomers, same exact formula, like all isomers, it's just the connectivity is different. Okay, so let's keep going. Okay, so question 3 is about functional groups. Let me drink some stuff. Are there any questions about isomers? Do we need another example about isomers? Throw it up in the chat while I drink my tea. Can I give an example of a conformational isomer? Yeah. Okay. So for example, a conformational isomer, boop, like that. Can we name that? That's 1, 2, 3, 4 carbons. It's butane. But I decided to make it zigzag like that, right? Where we have a carbon there, 4 carbons in a row. Or, I mean, I don't have to draw it like that. I could draw it like 1, 2, 3. This still works too, right? With our whole idea of the whole idea of, ends or joints in a skeleton structure mean that we have a carbon atom. These two molecules are the exact same. All I really did was kind of just rotate this molecule, or sorry, rotate that bond down. These would have the exact same name because, the whole deal with names is I go 1, 2, 3, 4 carbons, that's N-butane. But I could also say that the longest chain in this molecule is 1, 2, 3, 4. It's still N-butane. So this would be an example of a conformational isomer. What else? Let's think of another one. Oh, I have an example. I did this in office hours, so I'm sorry if you were in office hours and you have to see this again. But let's say I have 2 molecules. So let me move this guy, move you. I have this molecule and this molecule. Are these molecules related at all? I mean, if you looked at that really quickly, you'd be like, yeah, they're way different. They can't be isomers. Don't be lazy. Get the chemical formula of both of them. All right. So let's go and look at the chemical formula here for both of these. So each of these joints or ends is a carbon. So this is C4, right? Let's get the hydrogens. 1, 2 coming off of that carbon because there's already a double bond. So I just need 2 hydrogens. This carbon only needs 1 hydrogen because there's a double bond and a single bond. So that 1 hydrogen makes 4. This carbon has 2 hydrogens and then this one has 3. So there's a total of 1, 2, 3, 4, 5, 6, 7, 8. So C4H8. Okay, let's go look at the other one. All right, so this also has 4 carbons, 1, 2, 3, 4. Okay. Again, predict the number of hydrogens. So each carbon's only bonded to one other carbon. So each of those carbons has 2 hydrogens. Guess what its chemical formula is? C4H8. So they are isomers. So throw it up in the chat. What type of isomer is this? Is this conformational? Can I turn this molecule into this molecule by just rotating bonds? Throw it up in the chat. No, yes, no, we can't just like rotate it to make them match. No, they're structural isomers. So don't be lazy. Okay. And just look at, like, even me, I can't just look at 2 molecules and be like, yeah, those are isomers. No, I actually have to write out the chemical formula and figure out what it is. And so in this example, it's not super intuitive to see that, hey, yeah, these are isomers of some sort, that they look like one another. They don't look anything like one another. And so, really the tried and true way is to actually compare their chemical formulas. Because if we look at these two, yeah, you might, if you look at these, you go like, yeah, there's a ketone and a methyl group on both of those. They're isomers because all we're really doing is kind of moving this group from one position to another. That's, you're just ripping one off, putting it somewhere else. That's structural. But in this case, the connectivity is different. They're structural isomers. So don't get lazy. Okay, even I can't just look at something, 2 things, and be like, yeah, those are isomers. I have to kind of play around in my head to see, to compare them. All right, I'm trying to think of another structural isomer here. Even another one like, so if I had something like this, or if I drew it like this, I guess like that, those are conformational isomers. They're the same molecule. You can just rotate things or rotate things or bend them or flip them, and they're the same molecule, the exact same. They would have the same name. Or if we had something like this, and so that's butane, and let's say we had a ethyl group come off like that, off of carbon 2. I could also draw, like if I told you to draw two ethyl butane, maybe you would draw it like that, like going the other way. Those are conformational isomers. They're exactly the exact same. They would have the exact same name in those cases, because so for the structures have to be the same. Yes, they have to be the same. They have the exact same name. But for structural, they can have the same. No, for structural isomers, they will never have the same name. Structural isomers will not have the same name. So these ones, like we didn't name alkenes, but this is an alkene, and this is a cyclobutane. Like these will not have the same name. These are structural isomers. They do not have the same name. These two molecules also don't have the same name because these two substituents are 1,2, and this one would be 1,3. So they're different names. Conformational isomers will always have the same name. Okay, does that clarify it? Okay, all right. So let's keep going. So functional groups. So I have, some functional groups here. So I have a lot of them listed here, so we can kind of go through them. So with functional groups, remember, there's two schools of thought here. One, what are functional groups? They're anything other than just alkanes, things other than just like carbon lines. We want to find other things. If you are raising your hand, I don't think you can unmute yourself, so you have to write it in the chat if you have a question. So functional groups here, we want to look for things that are different looking. And in my head, there's two types of functional groups we can have. There are functional groups that have carbonyls attached to them. So a carbonyl is anything that has a carbon oxygen double bond in it. So we see a couple of those in here. So there's a group of functional groups that have this type of structure, this oxygen carbon group in it. But what makes them all different is what is attached to that carbon in the carbonyl. So in this case, like if we look at that carbonyl, that carbon is attached to a nitrogen. Can we go over chapter 6? We did that a little bit in class, so I still want to go over a little bit more of chapter 4. So we have this carbon on carbonyl attached to a nitrogen. So this is an amide. So there's an amide and then there's an amine. Both of those functional groups have nitrogens associated with them, but the amide has a carbonyl that's adjacent to it. So this group is an amide. While other nitrogen containing groups have this nitrogen, see how we have a nitrogen with nothing else attached to it? This is an amine. So be very careful and don't just look at this NH3 and be like, oh yeah, that's an amine. No, you have to see what is attached to it. So in this case, this is an amide. You can't double count it and say it's an amide and an amine. You can't do both. If we had a molecule that just had this in it, it only would have the amide functional group, not amide and amine. So that's a common mistake. Or like a student might say, oh, this is a ketone and an amine. That's not correct. Ketone would be something like this molecule where we have a carbonyl, but then that carbon of the carbonyl is attached to two other carbon atoms. So that would be, this is a ketone. This molecule or this functional group, this would be a ketone. All right, so we got our amide, our ketone, we have an alcohol, there's our OH. Actually, we have a bunch of alcohols here, so let me get a different color. So we have OH, there's an OH here, OH there, and an OH there. So bunch of alcohols. So you can determine what type of alcohol it is. This alcohol is a secondary alcohol because the carbon it's attached to is attached to two other carbons right there. Oh, you can't see that. So this carbon is attached to two other carbons, so it's secondary. This OH over here, that alcohol is a tertiary alcohol because it's attached to three other three other carbons. You're right, Allie. This is a phenyl. So we actually, you're right. I got a little too crazy with my highlighter. So this is an alcohol, but because it's attached to a phenyl ring, or sorry, an aromatic ring, this whole thing is called a phenyl group. So kind of like we're identifying like tertiary, secondary, etc. This is like a specific type of alcohol because it is attached to an aromatic ring. So we consider that phenyl. And so, we have another carbonyl here. All right. And so another carbonyl, carbon oxygen double bond. We inspect what is attached to this carbon. It's just two other carbons. So this would be also another ketone. And then finally, the last thing, this is an alkene. So there's just like a random, there's actually two random double bonds. So there are two other alkenes in here. So if you circle these, everyone already has access to the key. We have an alkene, we have some alcohols, a phenyl. What else do we have? We have an amide and an amine. All right. So it's these ones, the ones with the carbonyls and things attached to it are tricky. Yeah, so we don't have, Sydney, we don't have an aromatic. Well, we do, but because it's attached to an alcohol, we don't double count it, right? We call this whole thing a phenyl. We call this whole thing a phenyl, and because there's an OH attached to it. So we don't double count it and say that we have a phenyl and an aromatic, unless we actually did. If we had like some, I don't know, something, some bond, and we had an aromatic ring over here somewhere else, then we would have an aromatic and a phenyl group. But because this aromatic is associated with an alcohol, we just call it phenyl. Oh, and did I not circle ketone? Yes, and so ketone would be our last one there. Okay, all right, so let's do another one. So again, with carbonyls, do not double count them. Do not double count them. So I like to kind of get the carbonyls out of the way first. I locate them. So right here we have a carbonyl, and I ask myself, what's attached to it? What weird thing is attached to it? So here we have a carbonyl that's directly attached to an OH group. So this is a carboxylic acid. Carboxylic acid. So do not say that we have a ketone and an alcohol. That is incorrect. Because these two groups are attached to one another, it makes it a carboxylic acid. That's a common mistake. Just like we said with the carbonyl and the nitrogen, that's called an amide. It's not a ketone and an amine separately. Because they're together, we have a new type of functional group, right? So there's some weird stuff. That's just a CH3, it's just a carbon chain. Here we have a ring, we have an OH group right here. All right, so this is not attached to an aromatic, it's attached to a ring, but it's not our aromatic ring. If it looked like that, then this would be a phenyl, but because it's just attached to a ring, it's just a secondary alcohol. All right, so what else is here? We have a triple bond. This is a triple bond, so this would be an alkyne. We have a double bond. This is an alkene. And then the last thing that's kind of weird and not just a carbon would be this group right here. So we just have an oxygen kind of like in the middle of a molecule. So we have an oxygen attached to two other carbon atoms. So this is called an ether. All right, so that's an ether. And so, yeah. And then other than that, like identifying groups, that's basically all I can really, identifying functional groups on like a complex molecule like this is really all I can ask you on the exam. I would never in a million years ask you how to name this. I don't even know how to name it. All right. Okay, so would we classify alkanes? So alkane is like the vanilla base flavor that we're working with. So yes, there are alkanes in here, but every molecule is going to contain alkane. So we don't typically classify that. It's like assumed that that's what you start with. We have some type of carbon chain that we're building on top of. But yes, you can say we have alkanes here. Why is alkyne the CH? It's not. The alkyne is actually the triple bond. The triple bond. So all of these lines indicate carbon-carbon single bonds. Those are alkanes. This bond, although the carbons aren't drawn, we have a carbon-carbon double bond. So that's an alkene. Here we have a carbon-carbon triple bond, so that's an alkyne. Okay, I could do the alcohols. When do we need to know disulfide and carboxylate? Of course you do. Oh, make sure when you're writing in the chat, can you just say it to everybody? Can you make sure that you have your messages set to everyone so that everyone can see the questions, just in case I don't read it, all right, out loud. So if you're gonna ask a question, make sure it just goes out to everybody. Okay, so yes, if it's on the list, you have to know it. All right, if it's on the handout, if it's in the textbook, you need to know it. All right, so the question was primary versus secondary and tertiary alcohols. The trick is with alcohols, we have an OH group. What does O minus mean on the phosphate functional group? It means that it's an oxygen without a hydrogen on it. So it's an O minus charge. So for example, carboxylate is essentially a carboxylic acid that doesn't have a hydrogen on it. So you have an oxygen with a total negative charge. All right, so alcohols, we have an OH. So to figure out whether it's primary, secondary, or tertiary, you want to look at and see what is attached to the carbon that the OH group is attached to. All right, so you look at this carbon that the OH is attached to, and I see that it's attached to 2 other carbon atoms. So that's what makes it a secondary alcohol. So I like to think of primary alcohols are always on the ends of chains. So like here, this is a primary alcohol, because if you look at the OH and you look at the carbon it's attached to, it is only attached to 1 other carbon. Do you see that? It doesn't matter how long the chain is. If it's like that, if it's on the end, it's a primary alcohol. Doesn't matter how long the chain is, because the carbon it's attached to is only attached to 1 other carbon. So that's primary. Secondary will kind of be in the middle of a molecule, so it'll look like this. So just like this one that we drew over here, but it just so happens to be in a ring, but this one is also a secondary alcohol, because if you look at the carbon the OH is attached to, it's attached to 2 other carbon atoms. So this is a secondary. And then finally tertiary, which we don't run across as much. So we have a OH group coming off of this, but then we also have another carbon atom. So if, again, we look at the carbon atom the OH is attached to, and I see, oh, there are 3 other carbons attached to that group. So this is a tertiary, right? So do double bonds affect alcohol classification? I don't know what that means. The only types of alcohols are, again, it has an OH and it can be anywhere in the molecule, or a phenyl is specifically a alcohol that's attached to a benzene ring. I'm not sure what that question is referring to. If we go back to this one, this OH, if we look at it, is a tertiary, because if we look at this carbon atom, there is 1, 2, 3 other carbons attached to it, so it's tertiary. I think all alcohols are single bonded. Oh, we'll be together. Yes. So you won't have, is that what the question is? If it was like this can't happen. Like if we had, some like this won't happen. Like a double bond oxygen to a carbon, that won't happen. What you might be referring to is a carbonyl. Carbonyl is a carbon oxygen double bond, but note there's no hydrogen here. There's no hydrogen attached to that oxygen, so it's not an alcohol. It is it's one of our carbonyl containing functional groups, and specifically this is a ketone. Okay, if it's a carbon attached to a double bond, yeah, we don't make that distinction in this class. So if you just have an alcohol like this and then there's like a double bond somewhere, it's still an alcohol. Okay, so all right, so we're gonna do another one. Yes, so this one, what is this? We see a carbonyl, right? So we go to our carbonyl containing functional groups. In your mind, you should have 2 different things in your head. Carbonyl container, yes, it's an ester, because we have our carbonyl carbon is attached to an oxygen. So this is an ester, and that's the only thing here. So just kind of like going through all of those carbonyl containing compounds, I like to think of it as, okay, the simplest one that we can have, and it's like attached to something. The simplest one that we can have is an aldehyde, where we have our carbonyl carbon and there's a hydrogen attached to it. All right. Or we could have a carbonyl and there's two other carbon or two other R groups attached to it. So just other carbons. So this is kind of like a carbonyl in the middle of a molecule. This is a ketone, right? So those two. So it's either, is it a carbonyl in the end, or is it a carbonyl in the middle of the molecule? Or we could have a carbonyl carbon, and there's other stuff attached to it, and we have an OH on the end. This is a carboxylic acid. Related to that, if we take off that hydrogen, and remember, hydrogen is positive charge, so we have a total negatively charged oxygen there. This is specifically a carboxylate. So it's essentially the ion form of the carboxylic acid. When making molecular formula to find hydrogen, can you do, no, you can't. That's only for straight or branch chained carbon chains. It does not work if it's in a ring, or if there's double bonds, or if there's triple bonds. I suggest, Lauren, what you do is you just count them and determine how many hydrogens are on each carbon, and you will always be right. Yes, there are little tricks that you can do if something is a straight chain or a ring, but I find that memorizing little formulas and knowing when to use them is I think more difficult than just knowing that carbon always makes 4 bonds. So no, that equation does not work all the time. Okay, so there's carboxylate, carboxylic acid. So other types of things that can be attached to a carbonyl carbon. So we have OH, we can take off the H to make a carboxylate, or with that O, we could have other R groups, like a chain, like a carbon chain attached to it. This is an ester. So you did this in lab, right? Where you have this carbon, oxygen, and then a bunch of carbons on the end. That's an ester. And then other things other than oxygen, we can have carbon, double bond O, with some nitrogen and stuff attached to it. This is an amide, all right? And I think that's it. Is that all of them? I think that's all of them. Amide. Yes, that's all of them. All right, so those are functional groups. So let's keep going. All right, so let's name this molecule. So let's name it. Naming this molecule, so I see it's a ring. It's a ring, so that's probably the parent structure. So with naming any molecule, the big thing is first finding the parent structure. So the longest continuous carbon chain. So in this case, it's in the ring. There's 4 carbons in that ring, so that's the parent name. So the parent, this is cyclobutane. But now we need to name the stuff that's around it. So the stuff that's around it, we have 2 methyl groups around it. All right. So I can just name it kind of, just 1, 2, 3, whichever way. So I see that the methyl groups are on carbons 1 and 3. So I can call this 1,3 dimethyl cyclobutane. So 1,3 dimethyl cyclobutane. But what's a little bit tricky here is that I have indicated stereochemistry here, that you see some wedges and dashes. So I'm trying to convey to you, like I have a square, like a flat square. One of the methyl groups is going up and the other one is going down. So these 2 substituents are trans to one another. If you like look at the molecule from the side, right? That one of the methyl groups is going to be going up and the other one is going down. So this is a trans 1,3 dimethyl cyclobutane. So don't, finish just at 1,3 dimethyl cyclobutane. Make sure that you indicate the stereochemistry. And so just for fun, let's see if we can't draw the cis isomer. So the cis isomer, it's the exact same connectivity. It's just that the bonds differ, the substituents differ in 3-dimensional space. So if we wanted to draw the cis isomer, it's the exact same molecule. It's the square. And then for fun, I'll just put both of them up like this. This would be the cis isomer, CH3, CH3. All right, so you can see that both of those bonds are going up, and that would give you the cis isomer. Or you can, if you're at home doing this, trying the cis isomer for yourself, you might have pushed them down. You might have put those two groups facing down, but these are actually the same the same molecule. All right, both of these are cis. They're not different molecules. If you just try to flip, if you just flip one of them, right? Like this is a turtle on its back with its feet hanging up. All right, this one, its feet, the turtle's feet are down. So you just flip the turtle upside down on its shell, and they're both the same molecule. And so for fun, let's get the molecular formula of this one and this one. All right, so we have the skeleton structure. Let's get the chemical formula. So determine how many carbons are in the whole molecule. So we have, I'll put a dot, 1, 2, 3, 4, 5, 6. So there's 6 carbons there. So let's find the hydrogen. Some of them are already there for us, but let's go through all the carbons. So this carbon has 3 hydrogens. So does this one. The ones in the ring, there's 2 hydrogens here, 2 hydrogens there. Be very careful with these ones. So this carbon already has 3 bonds. So there's a hydrogen there and there's a hydrogen there. All right, so total, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is C6H12. So Lauren, does that fit our formula? No, it doesn't, because this isn't a ring. All right. And then for fun, let's also do it for this molecule too, because I just told you we have cis and trans isomers, so they should have the same chemical formula. And we will prove to ourselves that they do in fact have the same chemical formula. So carbon, carbon, so 6, right? So 6 carbons, 6 carbons. And then let me erase those numbers. Let's get those hydrogens. So we have 3 there, 3 there, 2 carbons in these, or sorry, 2 hydrogens on those 2 carbons, and then 1 hydrogen there. So if you count all of those hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So both of them have chemical formulas of C6H12. And then maybe for fun, so these are isomers, specifically stereoisomers. If we could draw a structural isomer of one of these molecules. So a structural isomer would have this chemical formula, but the connectivity would be different. So an example of a structural isomer of this molecule could be something like this. Cyclohexane. Cyclohexane actually has the chemical formula C6H12. The molecule looks completely different, but they are in fact structural isomers because the chemical formulas are the same. Another one that's C6H12 could be 1, 2, 3, 4, 5, 6, something like this. That is also C6H12. If you count it out, that's an alkene with 6 carbons, so hexene. You don't need to know how to name it, but that is also C6H12. Okay, so let's keep going. All right, so let's do a couple hard naming ones. I like this one. Okay. Condensed formulas are hard. It's easier when you can like see all of the connectivity, you see all the carbon chains, it's easier. Like, yeah, this is the ring, you name the ring and you name the substituents. But when it's all like this, all in a line, it's hard. So so there's a couple ways you can do it. You can either redraw it so it looks like a line skeleton structure. That's probably what I suggest. Or you can kind of go through each carbon and figure out what's attached to each carbon. So with condensed structures, we try to be clear of and showing where's the carbon chain. So that's what these lines are indicating, what is attached to what. So if we think about our carbon chain, we have that carbon attached to that carbon, attached to that carbon. This CH3 is in parentheses. So that means that this CH3 is attached, like dangling off this carbon. So if again, we're looking for the longest chain. So we have that carbon and that carbon. So we have 1, 2, 3, 4, 5 carbons in a line. So you can draw that 1, 2, 3, 4, 5. Oh man, 1, 2, 3, 4, 5, right? So 4 carbons and, or sorry, 5 carbons in a chain. So let's draw out the other substituents that we haven't, identified yet. We have a fluorine and it is attached to carbon 2. So I will draw that. We have carbon, fluorine, carbon 2. Right. Then it looks here, we have a carbon and then there's a CH3 attached to it. So a methyl group. And so it's coming off of carbon 3. So this is what the molecule actually looks like as a skeleton structure, which might be easier for you to name, because now I can see it clearly. We have 1, 2, 3, 4, 5 carbons in a chain. This is pentane. All right. And then we name the substituents. We have a substituent there and there. All right, so this, if I kind of number them 1, 2, 3, this is 3 fluoro. Oh, so no, it's 2 fluoro, sorry, 3 methyl. And that's it. So it's 2 fluoro, 3 methyl, pentane. That's it. All right, so do yourself a favor and just take the time and actually draw out, a structure that you can more easily, picture to help name something. And I like these structures a little bit better when trying to find chiral carbons, because I think that's one of the questions too. How many chiral carbons are in this structure? So chiral carbons, the requirement for chiral carbons is you need a carbon with 4 different unique attachments on it. So I just go through each carbon individually and think, okay, are there, like, how many hydrogens are on it? Because like this leftmost hydrogen has 3 hydrogens on it. So you can just forget that one because it can't have 4 unique groups on it because it already has 3 hydrogens on it. So anything with 3 or 2, any carbon with 3 or 2 hydrogens can never be chiral. But if we go to the next carbon, if we look at this carbon has a methyl group. It has a fluorine group on it. It has a hydrogen that is implied because it needs 4 bonds. And then it has this stangly bit off of it. So this is a chiral carbon. That carbon is chiral because there are 4 unique things attached to it. So if we go to the next one, right, this carbon, again, ask yourself what is attached to it. What is attached to it? We have a methyl group. We have an ethyl group, and then we have this other group that has a fluorine on it. And then what's missing here is a hydrogen. And so this is also a chiral carbon. All right. And so the last thing here, let's just pretend that, let's say that this bit had 2 carbon chains on it. Let's just for like a minute. If this carbon had an extra, if this methyl group, the substituent had an extra carbon on it, it would be an ethyl group, then that carbon would not be chiral. Because if we kind of focus on that carbon atom, we have a hydrogen, we have this weird fluorine thing, but then we would have 2 groups hanging off it that are exactly the same. We have 2 ethyl groups kind of floating, hanging off of it. So this then, if this was an ethyl group, then it wouldn't be chiral. All right, so that's how we kind of inspect chirality there. All right, do we want to do another one? Do you want to do this one? Let's do this one. Yes, okay. So again, find the longest carbon length, carbon chain. It's not always the direct path. Actually, I'm going to tell you in this class, it'll never be the direct path because that's too easy. So find the longest carbon chain. You might mess up. That's fine. Just it's like a maze. You want to find the longest path here. So straight across 1, 2, 3, 4, 5, 6. So 6. Okay, but I'm going to delete that and see if there's any longer paths than 6. So I'll start up here. 1, 2, 3, 4, 5, 6, 7. So that's 7. All right, so that's a little bit more. But there's other paths that I can take. So let's check that out. So that's 7. 1, 2, 3, 4, 5, 6, 7, 8. So there, that is the longest path, 8. All right, again, not always the most direct path. And what I mean by longest carbon chain, we want the carbons to be singly bonded to one another. So that's why I end here, because this carbon isn't attached to anything else that I can't keep going. Or like this carbon, I start here because it's on the end. So we're going from end to end here. So I've identified the longest chain. There's 8 carbons. So then I think what's hanging off of it? I have a methyl group there. a methyl group there, and a bromine group there. And so I want to make sure that I name all of those, indicating what carbon number they're at. So I know 8 carbons means octane. So that's my parent name. Now it's a little bit of figuring out how to number things. So the numbering for this one, yes, Lauren, it says, so basically follow a path without lifting a pencil. Yes. So yeah, why don't we do that real quick? So like you can't go like this and count these, that you can't like double cross. Like that's not a continuous carbon chain. We have to look at something like that. So that's the longest carbon chain, or, like that, again, not lifting the pencil to try to get between different carbons, or I can't do something like I don't know, like that. You can't do something crazy like that. You want to find the longest number of carbons you can put your pencil through without lifting your pencil. All right, so sorry about that. So let's go back to what I had. Blah blah blah. Methyl, bromine, methyl. All right, so numbering. Numbering kind of also like trying to find the longest path. Write some numbering in, check that one, and then do it the other way to see if you can't minimize your numbers. So the way we number our substituents is we always want to minimize the numbers. Like you always start on the side of the molecule that has the most substituents already, because we want to have low numbers as our substituent numbers. So for fun, let's just do it both ways. So I'm going to call that carbon 1, 2, 3, 4, 5, 6, 7, 8. So if I number it this way, I have something on 3, 5, and 6. 3, 5, and 6. So let's do it the other way for fun. So I'll do it in pink. So 1, 2, 3, 4, 5, 6. I don't have to keep going. So if I number it this way, actually, I have a substituent on 3, 4, and 6. So before I had 3, 5, and 6. This way I have 3, 4, and 6. So 4 is smaller than 5. So I actually want to take the pink path here. So if I do the pink path, this would be 3 methyl, 4 bromo, and then 6 methyl. But I want to combine those methyl groups and say 3, 6 dimethyl, so I can combine them. So the whole name for this would be, we start with bromo because B comes before M in the alphabet. Even though we say dimethyl, the di or tri or tetra, it doesn't count. It's the name of the pure name of the substituent. So we want to put the 4 bromo first. 4 bromo. And then it's 3, 6 dimethyl octane. That's the whole name. It's a long one. All right. And then what else is this question asking? I think it's asking for chiral carbons. So we can do that too, because chirality can be tricky. But the trick is anything that has more than 1 hydrogen on it already can never be chiral. So there's a bunch we can just disregard, like this one. These can't be chiral. This can't be chiral. This carbon can't be chiral because there's 2 hydrogens. That one can. It can, but it doesn't mean that it is. That one can't, that one can't, that one can't. So we've narrowed it down to 3 carbons. All right. So again, you want to put yourself in the shoes of that carbon and ask yourself, what is attached to you? I have a hydrogen, a methyl group, an ethyl group, and then this spaghetti over here. So this carbon is chiral because there's 4 unique things on it. Next, let's look at this carbon. So this carbon has a hydrogen, a bromine. It has 4 carbons over here and 5 carbons over there. So this carbon is also chiral. All right, so the next one, this carbon is also chiral because we have an ethyl, a methyl, and then this stuff over here. So this is also chiral. But let's just, humor me for a second. Let's pretend that this group wasn't CH3. Let's say it was CH2, CH3. All right, so if we again look back at this carbon, it has a hydrogen, it has this spaghetti over here, but then it has 2 ethyl groups on it, that very exact same. So if it was this, then this carbon would not be chiral. So there we go. All right, so, but it's not. There we go. All right, do we want to Do you want to just finish it? Yeah, let's just finish this. So when we have rings, typically the ring supersedes the parent structure name. Typically it's the ring because that can be our longest continuous carbon. So this ring has 1, 2, 3, 4, 5, 6, 7 carbons in the ring. So if this was like a regular straight chain carbon, it would be called heptane, but because it's in a ring, it's called cycloheptane. All right, and then we just name the substituents. So we have 1, 2, 3, 4. So this would be a butyl group, right? Butyl group. And then these two substituents, we have 1, 2, 1, 2. So this is diethyl. There's 2 ethyl groups there. All right, and so now it's numbering. So numbering, this one's a little bit tricky because it's 1, 2, 3, but the question is, do I want to go this way 1, 2, 3 or this way 1, 2, 3? So typically whatever name is first, so in this case butyl, like that, we'll name butyl before we name ethyl. We want to put that one as carbon number 1. So 1, 2, 3. So this will be called 1 butyl, 2, 3 dimethyl cycloheptane. Oh, sorry, I forgot the T. Heptane. There we go. So, okay. So, next it would be finding chiral. Why do we number butyl first? It's because the question is, well, we always want to minimize numbers. So there's really no difference in naming it this way versus this way. It would still be 1, 2, 3, 1, 2, 3. But we pick this way because butyl will be named first in the name regardless because it starts with a B. So we want that to start with the 1. We don't want to call this, we don't want to start the name with a 3 when we can start it with a 1. Yes, it is diethyl. Diethyl. Yes. Why is it butyl, not butane? Because butyl is a substituent. So butane is if it were a butane is when it is a parent chain. So make sure that you're writing to everyone so everyone can see the questions. Okay. All right. Okay. And then the question is, what is a chiral carbon? So right off the bat, we can just say none of these carbons that don't have something like weird attached to it, those aren't chiral because they all have 2 hydrogens on them. It's these 3. So if we kind of look at it, this carbon is chiral, this carbon is chiral, and that last this carbons 1, 2, and 3 are all chiral. Other than that, like that is what I would ask on an exam, like how many chiral carbons are on this structure. I would never ask you to name it. All right, so you can't add the chirality to the name. That's not something that's outside the scope of this class. Oh, and I forgot, all of these carbons also not chiral because they're either 2 or 3 carbons within that chain. Okay, so let's keep going. Okay, so we're an hour in, and I think we pretty much done with chapter 4. So actually quickly this one, if you downloaded, so we don't need to number substituents. We don't need to number substituents. What do you mean? We numbered them. 1 butyl, 2, 3 diethyl cycloheptane. You always number substituents when you're trying to tell the reader where they are on the structure, because like, are they here, here, or here? We don't know. Yes, substituents always end in YL. Okay, so this one, let's just see if we can't find the longest chain again. Whoops, sorry. Not always the direct path. You know, it's really easy to say like, yeah, 1, 2, 3, 4, 5, 6 carbons. This is hexane. If you downloaded an old version of the key, I actually had this one wrong. Sorry. So make sure you get the updated key. So the longest path, putting your pencil through as much carbons as possible without lifting your pencil is actually this way: 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 carbons right there. So it would not be something like going this way. I think that's 1, 2, 3, 4, 5, 6, 7. So that's not right. Or 1, 2, 3, 4, 5, 6, 7. That's also not right. It's this chain would be the longest. So this would be nonane. Specifically, it would be 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It would be 5, 5, or no, sorry, 5-ethyl, 5-methyl nonane. That's what it would be called, because we have a methyl substituent and an ethyl substituent coming off of carbon 5. Okay, so all right, so let's move on to the suggestion was chapter 6. Chapter 6. All right, so let's start here. Let's look at all these alcohols in this group and classify them as primary, secondary, or tertiary. All right, so these are all alcohols. So the idea is you want to look at the carbon that that alcohol group is attached to. So here we have 3 alcohols that we need to inspect. Again, this is a Lewis structure. It might be more difficult for you to kind of see it. So again, you have the time. Maybe you could go in and actually draw what the skeleton structure looks like. You have a 3-carbon chain, so it would look like that. And then you have an OH group attached to all of those carbons. So it'd be OH, OH, OH. So these 2 molecules are the exact same. All right. And then the question is, you go through each alcohol. And so you kind of focus on that carbon atom right there and ask yourself, how many other carbons is it attached to? This one's only attached to 1, so it's a primary. Also, this alcohol, kind of the flip side, because this is a mirror, the molecule symmetric. This is also a primary alcohol. But then if you look at the middle one, that OH group is attached to 2 other carbons. So this is a secondary alcohol. So this molecule has 2 primaries and 1 secondary alcohol in it. Total of 3 alcohols, but we can classify them a little bit differently. All right, so let's classify these monosaccharides, so sugars. So when we think about sugars and monosaccharides, we have 2 different types. We have aldoses and hexoses, or sorry, aldoses and ketoses. So meaning whether we see a ketone or an aldehyde, excuse me, functional group in the sugar. So again, if you are still unsure on functional groups, I don't know what to tell you at this point. So this structure is showing me a ketone because I see the carbonyl is in the middle of the molecule, that we have 2 carbons attached to this carbonyl. This is a ketone. So this means that it's a ketose, that the name will start with keto, and then we name the number of carbon atoms, and then we end it with ose at the end. So we identified it as a ketone, so we just count how many carbons are in the chain. So there's a carbon there, then there's a carbon right here in the ketone, so make sure you don't forget that. So there's 1 right there. So that's 2, 3, 4, 5, 6. All right, so 6. So this would be called keto hexose. So ose means sugar. Why do we not say, so this is classifying. So in the next question, it's actually the same sugar, and I ask you to identify it. This is identify it. No, we do not. When we're classifying, when we say like aldohexose, aldotriose, aldotetrose, we don't say D or L. All we're trying to say is that, hey, there are 6 carbons in a chain, and it's a ketone sugar. When we classify, we don't use the D or L, only if I'm asking you what kind of isomer it is or the identity. So in the next question, we say D or L, but we don't typically say, like in this case, it would be L. We don't say L ketohexose. We just say ketohexose to say that there are 6 carbons in the chain, and it's a ketone. Right, so we don't use it in this question, but in the next one, we do need to identify whether it is L or D. All right, so was that clear that this one, we do not say D or L at all, because we're just classifying it. We're just saying how many carbons and what functional group it is. But on the next one, we do. Okay, because we're trying to actually identify the sugar. So in this one, I'm trying to identify, and I give you options, right? I give you all the D monosaccharides and all the L monosaccharides. So just right off the bat, you can eliminate half of them by just identifying whether this is D or L. So throw it up in the chat. What oh, is this the wrong one? Give me a second. Oh yeah, you can't do this one. Crap. So this is not fructose. Yes, this is not fructose. My Googling did not do a good job Googling. I'm sorry. So those of you out there, can you change? This is not fructose. It was supposed to be. This is supposed to be a hydrogen. Oh, wait. Hold on. Man, this is really wrong. I'm sorry about that. Okay, I'm just gonna, okay, so. Okay, so this group is supposed to be an OH. This one is supposed to be a hydrogen. This one is supposed to be an OH. Sorry, all of these groups are flipped. That's what it's supposed to be. I'm sorry that I should have been more careful about this. So this is L-fructose. That's what I was supposed to try to get you to say. That one, we know that it's fructose because it is a ketone. All right. And then that the last OH is on the left side. The last OH that's on a chiral carbon is on the left side. So these three carbons are chiral. And so the LDL designation is always looking at the last chiral carbon. So regardless that the structure I put up here is incorrect, it's not a ketone or a ketose that I asked you to memorize. It's a different one. And it's not fructose. It's this isomer regardless is a L isomer because that last OH group off of the last chiral carbon is on the left side. Right. So it's an L something. So in this case, we look at how the OHs kind of arrange themselves. And so it is L fructose in this case. But regardless, you could have recognized that it is an L isomer and it's a ketone. So the only ketone sugar I asked you to memorize would be fructose. So this is fructose. For fun, let's just remember what D glucose and mannose looks like. All right, so D glucose and mannose, they have 4 chiral carbons in it. So this is CHO, and then this is C2OH. So that last carbon is not chiral on these two molecules. So both of them have the same structure. It's just how do the OHs, how do those stereogenic carbon centers differ from one another? So I know mannose, and remember, both of these are the D configuration. So the OH has to be on the right side. The last one has to be on the right side. So mannose, I always like to remember it has like 2 on the same side and then 2 on the same side, and then the rest are hydrogens. So it would be left, left, right, right. And then glucose, is right, isn't it right, left, right, right? So it's OH, 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 OH. I'm pretty sure that that is glucose. Sometime I'm not 100% sure. Glucose, D, glucose. Yes, okay. Oof, oof, okay. And so I like to remember the D isomer, because if you get a question like this, and I would give you the correct structure, if you see the L form, I would just flip it automatically. And I don't mean flip it in my mind, I mean actually draw it and flip it, and then write out what the left right designations are for the D form, but then report the L form, because what we're reporting is the flipped one. All right, so these are glucose, mannose, and fructose are the 3 sugars that I'm asking you to memorize. All right, and so the trick is what is the order of the OH groups left or right on those chiral centers, those chiral carbons. And so what is not shown here, I mean, I could have drawn, or that the other sides of those OH groups are hydrogens. And they are, all of those carbons that are in this kind of backbone, they're all chiral. You can prove it to yourself that they're all chiral, except the last carbon is not chiral because there are 2 hydrogens on it. So all of those rules still apply here. Okay, do we have to memorize the ring forms? No, you don't. That's too hard. That would be awful. All I want you to know is how to identify alpha and beta epimers. So if I give you a ring, can you identify it as alpha or beta? But you don't have to identify whether it's glucose or fructose. Okay. All right. So keeping in mind that we have chiral carbon centers. So that means when you do the L and D, do you flip all the OH? You flip all of them, yes. So the L and D isomers are perfect mirror images of one another. So they are enantiomers of one another. So you flip all of them. Or so you flip all the chiral ones. You don't have to flip this one or this one because they're not chiral. All right, so let's keep going. So on that same vein, the D and L isomers of fructose, for example, are perfect mirror images of one another. So we call those enantiomers, just like enantiomers that we talked about in chapter 4. Then we introduce this new term, diastereomer. It's kind of like a mirror image, but not completely. So a diastereomer is an incomplete mirror image where only some of the OH groups are flipped. So for example, mannose and glucose are diastereomers of one another because we could turn mannose into glucose by flipping just one of the carbon, the stereochemistry. So if we just flipped one of them, then we would make it look like glucose. So D-glucose and D-mannose are diastereomers of one another, that it's an incomplete mirror image. So in this question, it's asking for diastereomers. So we're looking for incomplete mirror images. All right, so we're flipping, this is the molecule we're focusing on. So what I usually do is like highlight the OH groups that I'm focusing on. How are they flipping in space? Again, we don't care about the CHO. That's the aldehyde because that is not a tetrahedral carbon. So that's not chiral. It won't be affected by being flipped by the mirror image. Only chiral carbons are. Or CH2OH. This carbon is also not chiral because it's not in this like checkered backbone, right? So this carbon's not chiral, so it's not affected by mirror images. So let's just highlight where those OHs are on A and B. So here on A, we see that it looks like just one of the groups flipped. So this is an incomplete mirror image. So A is a diastereomer. The next one, it looks like we have all the groups on one side. So we can make those match by just flipping one of the carbons. So B is also a diastereomer. Excuse me. And then finally, this last one, you see that it is a perfect mirror image. C is the mirror image. So this is an enantiomer. It's a perfect mirror image. So this would be I don't know what sugar this is. 1, 2, 3, 4, 5. I don't know what sugar this is, but I know that this would be the L form, while our original molecule here would be the D form. Whatever sugar it is, would be D sugar, and then this is L sugar because it's the perfect mirror image. Versus A and B, so this is the actual question. These are diastereomers because they aren't complete mirror images of one another. All right, so these two, all three of these sugars would typically have different names to them, but the original and C, since they're perfect mirror images, they would have the D and L designations in their name, whatever sugar it would be. It doesn't really matter what it is. Okay. All right, so next one. So is this the same question? No, it's not. So here's another sugar. I don't know what it is. It's 6 sugars. It's an aldose. I don't know what it's called because this one is left, 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 right. So not one that you have to memorize. So it's one of the other sugars. But this question is asking which is an enantiomer. So recognize that enantiomer means perfect mirror image. So we're looking for the perfect mirror image. So again, I just highlight the groups 1, 2. So left, 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 right. So A here is that. So again, not a perfect mirror image. We just flipped one of the groups. So this is a diastereomer. This would have a different name, like, I don't know, some other sugar name to it. Like, you know how we have glucose, mannose, fructose. So there's other sugars out there as well. And so it has another name that ends in ose. Then if we look at the next one, so 3, so right, 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 left. So this B is the perfect mirror image. Right, because the OHs, they're flipped. All of them are flipped perfectly. So this is the mirror image. So this would be an enantiomer of it. So B would be our answer. And then just for completeness, let's look at C. C is like that. And again, we just flip how many groups? It looks like we're just flipping one of the carbon centers. So this would be a diastereomer. So A and D are diastereomers. B is the enantiomer. And so just, whoops, I'm sorry, drive it home, these two sugars are isomers of one another, or specifically enantiomers. So we use the D and L designation. This one has the last chiral OH on the right side, so this would be D, and then this one would be L. But the question doesn't ask it, but we can look at it anyway. Okay. So, and they would have the same name, just D and L at the front for either of those. All right. So, how many more? Okay. Wow, we might actually finish all these. Okay, so which of the following monosaccharides would provide a positive Benedict's test? Oh, I'm getting tired. Okay, so Benedict's test. Oh, I should have capitalized that. It's like a person's name. And I think it's possessive. So the ideals of a Benedict's test, this is what I showed in class, is we started with a blue solution. That blue solution, the reason it was blue was copper plus. And so when we introduce a sugar to it and it reacts positively, what happens is we get that brick red compound. All right, what that is copper plus in the form of copper oxide. So that's that brick red solid that we saw. So we see copper in this reaction. It goes from that blue, clear blue solution to a red solid. So this copper substance going from 2+ to +1. So it is gaining electrons. So it is being reduced. The Benedict's test, when it's positive, copper 2+ is reduced to copper plus, where we see the red color. So this only happens when we introduce what's called a reducing sugar, meaning that the sugar is acting as a reducing agent. The sugar is actually being oxidized in that process. If we remember our oxidation reduction ideas, if copper is being reduced, then the other reactant, the sugar, is being oxidized. So therefore, the sugar is a reducing agent. So reducing sugars, they are able to be oxidized if there is a free anomeric carbon on that sugar. So long story short, all monosaccharides are reducing sugars because they have either an aldehyde or ketone available to do the Benedict's test reaction, that anomeric carbon can react with that copper 2+ and then become oxidized. So actually the answer is all of these. All of these will produce positive Benedict's test. The problem is once we introduce disaccharides or even polysaccharides, depending on how we do our condensation reaction to make our di or polysaccharide, if the glycosidic bond includes the anomeric carbon, then you essentially tie up the anomeric carbon and it can no longer be a reducing sugar. So essentially the only sugar that we care about that is not a reducing sugar is sucrose. So sucrose is not a reducing sugar. And the reasoning is because when you build a sucrose molecule out of glucose and fructose, the two anomeric carbons in each of those monosaccharide subunits, they're like kissing one another. That's how they're making their glycidic bond. That it's the two anomeric carbons are the ones involved in the bond itself. So it's not available to be a reducing sugar. So sucrose is the only non-reducing sugar that there is. There's not that many of them. And it's funny, sucrose, the most common sugar that we work with, it's table sugar. It's the white sugar you buy in the 5-pound bag. Sucrose is a non-reducing sugar. While all of these, glucose, mannose, lactose, all the forms, DL, everything, they are all reducing sugars. So they will produce a positive Benedict's test. But the criteria is that you need a free anomeric carbon, either as an aldehyde or a ketone. All right. Okay. So let's keep going. So which are D isomers here? So D means what? Left or right? Left or right? Correct. It means right. Oh, but like A lot of these are on the right. All right, so what carbon are we looking at when we look at D versus L isomers? What carbon do we look at? Do we look at the first one? Last chiral carbon. Very good. So it's the last one, not quite the last one, right? Because the last carbon on all of these is this carbon, right? But those carbons are not chiral. We are looking like specifically for the last chiral carbon, because actually in all of these, all of them are on the right, technically, but what we're looking at is the last chiral carbon. So this carbon that's in the weird checkered backbone here. So we see actually all of these OH. Sorry, I haven't gotten too creative with my questions, but I want to make sure that you're looking at the right thing. And in this case, it's the last chiral carbon. All of them are on the right. So we actually don't care at all of the other groups. We don't even care at all what those other groups are doing. We don't care. It's the last chiral carbon. And so all of them, because they are on the right side of the molecule, all of them are the D isomer. Okay. So the last question from chapter 6 here. So what type of polysaccharide contains this type of glycidic bond? So this is very similar to the one we did in class today, but it's the other one. So recognize how we build structural versus storage polysaccharides. All of them are made with glucose. All of them. All of them are made of glucose. It's just how they're used in nature. Are they being used for energy storage, or are they being used for like building cell walls in trees? They're all made of glucose, but what's different is the structure. So it's funny, you remember the secret to chemistry. It's composition and structure dictates chemical properties and behaviors. So in this case, structural and storage polysaccharides, they have the exact same composition. They're all made of glucose subunits, but it's their structure that's different. It's how they're actually linked together is different, gives us our different type of usage within our life forms here. So the first thing to this question is to identify, okay, what type of linkage is this? So, don't get too, overwhelmed with everything that's going on here. Basically, what you want to look at is the leftmost molecule and look to see how is that original OH group that was on this ring structure. So this is the glycosidic bond. It's this one. It's not this one. It's this one. We want to see how is that bond oriented relative to carbon 6 right here. So in this case, they are trans to one another. One's pointing up and one's pointing down. So this is an alpha glycosidic bond linkage. It's alpha. And then we can be really specific here and say the numbers if we want, but we don't actually need it to answer this question, but we can anyway. So for these rings, we always start counting at the anomeric carbon. So in this case, they're both on the right. So how we're forming the glycosidic bond right here, we want to name, okay, what is this carbon? And then what number carbon is this? So this is alpha 1 arrow, and then we name the other carbon. So I'll pick a different color. So we start on the anomeric carbon, which is always the right one. So the rightmost one. So 1, 2, 3, 4. We are building this glycosidic bond linkage between carbons 1 and 4. So specifically, this is an alpha 1, 4 glycosidic bond. All right. So, but we didn't need the 1, 4 part because what you should know with structural versus storage polysaccharides, all storage polysaccharides, those are like glycogen, what is it? Amylose, amylopectin. All of those have alpha either 1, 4 or alpha 1, 6 linkages. Amylose only is alpha 1, 4. Glycogen and amylopectin are both alpha 1, 4 and alpha 1, 6 to get like globular structures, but it doesn't matter because storage polysaccharides, when you're just taking the excess foods or nutrients that you're eating in the forms of sugars, storing them for later, those are all linked. All those glucose units are linked together via alpha alpha linkages. Structural polysaccharides, because you need rigid structures. This is what builds cell walls. You want rigid structures. So the linkage is actually beta, beta 1,4 instead. Can you talk about what we need to know about the idea of blood and carbs? Not that much. Don't worry about it. There really wasn't any question. If you note and see that there aren't any questions in if I give you the pictures of the blood the chemical markers within blood types, you should be able to recognize who can donate to who. Okay, so alpha, always storage, beta, always structural, basically. Yes, because beta, if you go back to the in-class thing, what you see with the beta structure, so this is an awful sugar. All right, so there's my sugar. Beta, okay, and there's my tail, there's carbon-6. Beta linkages look something like this. All right, so it's remember the direction of the bond, that the glycosidic bond is cis to carbon-6. So this would be beta, and because of the way that that's structured, when you put a bunch of them together, what happens is that this isn't an alkane or anything, but like how the glucose units stack together, how it is put together, it makes this rigid structure because they alternate their direction essentially. So you get this really rigid structure that is useful for things like cell walls, cellulose within trees, and those fast growing plants, and all of that, things that you want to be nice and strong and not flabby fat like you would see in glycogen storage vessels on your body. All right, so there we go. So this question is nice because it kind of tests two things. Do you know the difference between storage and structural polysaccharides, their structure and what makes them different, but also can you identify the glycosidic bond there? All right, so we still have 30 minutes left, so we'll go back to chapter 5. Let's do number 9. Okay. Let's do number 9. So this is a combustion reaction. So we're doing chemical reactions. So we talked about a lot of different chemical reactions here. And so one of them is combustion reactions, but we talked about that in chapter 1 as well, and balancing combustion reactions. So if you recall from chapter 1, the strategy we use for balancing combustion reactions is you always balance the carbons first with CO2 in your molecule. Then you balance your hydrogens in your molecules using H2O, and then you balance your O2s at the end, that's the last coefficient you put in. So the problem is that in chapter 1, I always gave you the chemical formula, but now I don't give it to you because we know how to build organic alkanes now. And so in this question, I'm kind of testing two different things. It's one, can you draw the structure? And then 2, can you get the chemical formula from its structure? So I'm asking you here, how many moles of CO2 and water result from the complete combustion of 1 mole of this 2,2-dimethylpentane? Report the sum. So my strategy here is to draw the molecule first. All right, so this is kind of the way I get around like drawing compounds. I have you report the combustion reaction from it. So cyclopentane, if we identify the parent name, dimethylpentane, we identify the parent chain, it's pentane. So means 5 carbons. So that's our longest chain. 1, 2, 3, 4, 5. There we go. But then we have some substituents we need to name. We have dimethyl, so 2 methyl groups coming off of carbon 2. So you can just name it wherever. So I'm going to say carbon 2 is right there. So I have 2 methyl groups coming off of it. So 1, 2. So that is my molecule. But it's not completely apparent. I can't look at this name and know what the chemical formula is, but I can figure out what the chemical formula is from this structure. So again, we have to use our idea that carbon always makes 4 bonds. So we have to go through each carbon individually and ask ourselves how many hydrogens are on it. So all these end carbons have 3. So that's 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Then this carbon, because it's already attached to 2 carbons already, has 2 hydrogens. This one also has 2, and then be very careful for weird ones like this. So take your time, put yourselves in the shoes of that carbon and look around. Look around. You're right there. You have a carbon there. There's 1. There's a carbon over there. There's 2. There's a carbon over there. There's 3. There's a carbon over there. There's 4. So this carbon already has 4 bonds to it. So we don't have to add any more hydrogen. So everything I've drawn in pink here is a hydrogen. Oh, I didn't get the number of carbons yet. So we have 1, 2, 3, 4, 5, 6, 7. So this is C7, and then H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 16, H16. All right, so there is our chemical formula. So now we need to burn this. All right, so we set up our combustion reaction. Combustion reactions, we take our thing, so C7H16. Combustion reactions, we always react with oxygen, and our products are CO2 and water. Okay, so now this is just a chapter 1 question. Balance the chemical formula, or balance the chemical equation. We balance the carbons first with CO2. We balance the hydrogens next, and then we take inventory of all of our oxygens and make up with O2. That's how we balance a chemical, specifically a combustion reaction. So I see here that I need 7 CO2s for it to be balanced. I have 16 hydrogen atoms, so I need 8 H2Os over there, and then I'd be done. So the answer here is 15, is the sum in front of carbon, or sorry, CO2 and water. I could ask you, I think it was like one of the questions on the homework, I could ask you, okay, well, what is the coefficient in front of oxygen? So in that case, you would have to completely balance it. So why don't we do that? Why don't we just balance the whole thing, just to remind ourselves how to do it? So we don't have the coefficient in front of oxygen. So to get it, what I do is count up all the oxygens I have on the product side, total. So there's a total of 14 oxygens on CO2, and then a total of 8 oxygens on water. And so if you add that up, there's 22 oxygens total on the product side. And so then I ask myself, how do I get 22 oxygens on the reactant side? Well, then I would have a coefficient of 11 in front of O2. Now everything is completely balanced. All right, so there's that. So this question, really good at, can you take a name, make a structure? So I specifically made a line structure or a skeleton structure because I just think they're easier. And then getting a molecular formula out of that, and then doing a combustion reaction, which we should already know. Okay, so let's keep going. Other types of chemical reactions we talked about, organic ones. So we've talked about a couple types of reactions, condensation and hydrolysis, that are types of decomposition and synthesis reactions, where either bringing molecules together to make one molecule, losing a water, or we're adding water and splitting 2 molecules apart. So water is involved there. So unfortunately, in this reaction, we have water involved as well, but there is an alkene associated with this. So we're adding water across a double bond. So this is a type of addition reaction. There's only 2 types of addition reactions we've talked about. So adding across a double bond, and that is hydration and hydrogenation. So hydration, we add a hydrogen, and hydration, we add a hydrogen and an OH, because total, that means water. But hydrogenation, we add 2 hydrogens across it. And so with hydration versus hydrogenation, you can kind of tell by its reactants what's being added. So in this case, we have we're adding water and acid we use to catalyze the reaction. So we should be able to tell that this is a hydration reaction. All addition reactions, which are hydration and hydrogenation reactions, involve alkenes, so double bonds. When we talk about hydrolysis and condensation, they typically don't involve double bonds at all. All right, so we're adding to a double bond to get rid of it. All right. Okay, so yeah, we should see that this is a hydration reaction. Also, what's kind of the tip here, right, is we're talking about major products. We only really talk about major products if it's a Markovnikov product or not, right? Where the hydrogen goes where there's already more hydrogens. That's only associated with hydration because we're adding two different groups to it. So there's another tip into knowing that this is a hydration reaction. There is no Markovnikov product in hydrogenation because we're adding the exact same group across the double bond. So if we look here and see the two different groups that we're adding, we have this OH, right, that's being added. So it's in two different spots. So you ask yourselves, okay, if the OH is there, that means the hydrogen was on the other, it's on the other spot. And so the Markovnikov product is the product where the hydrogen goes where there was initially the most hydrogens already before. So if we go back to our structure, there's a hydrogen here in this position, but there's not one here because this carbon already has 4 bonds to it. So what's missing here is this hydrogen. So that means our Markovnikov product, the major product, is A. Because we want that hydrogen where there's already more hydrogens previously. How do you know it's hydrolysis or condensation? So there's many examples within the back practice exams, but in general, condensation, you're taking 2 molecules and making it 1. Hydrolysis, you're adding water and you're splitting the molecule. Lysis means to split. So you're splitting a big molecule into 2 different ones by adding water. Okay, so A, the answer is A. All right, how much time do we have? Okay, 20 minutes. Okay, so let's keep going. So what is the name of the product that is produced after the complete hydrogenation of this reaction? So the things I note: hydrogenation, that is adding hydrogens. I'm adding hydrogens. And you might be asking, where do I add the hydrogens? Well, alkanes, just like carbons single bonded, they are really non-reactive. It's double bonds are reactive. So we don't care about all the rest of the molecule. All we care about is the double bond right here. All right. So we are adding, we're doing a hydrogenation, we're adding hydrogen atoms. So then the question is, where do they add to? So I like hydrogenations because they're a lot easier. We undo the double bond and then this molecule gains hydrogens on those two carbon atoms. So that's the new molecule. So we just essentially redraw the molecule, but without any double bonds. That's what a hydrogenation is, where we saturate the molecule with hydrogen atoms instead of having double bonds. So the molecule would just look like that, all single bonds. And so the question is here, what's the name? So this would be cyclohexane, but then there's a methyl group on it. So this would just be methyl cyclohexane, because it's all single bonds. I don't have to say 1-methyl because there's only one substituent on it. So it's assumed that's on carbon 1. So we don't even have to say carbon 1. So yeah, methyl cyclohexane. And then the question is, how many moles of H2 are involved in this reaction? It would just be 1 because we just have 1 double bond that we're hydrogenating. So for each double bond, we add 2 hydrogen atoms. But a hydrogen molecule, H2, it is 2 atoms. So we need 1 H2 molecule to undo one double bond. So if I had something like this, like that, 2 double bonds, and if I wanted to completely hydrogenate it, I would need 2 moles of hydrogen. So the question is, why doesn't the other H be attached to the bottom? It is attached. So I just got lazy. Okay, so if we go take back a step and ask ourselves what atoms are here, we have carbons. Okay, so what's already here, there's already a hydrogen right there. And then here there's no hydrogens. So when we add the 2 hydrogens from H2 to those bonds right here, okay, and then undo the single bond, and then when we redraw it, there is a hydrogen here and there is a hydrogen there, and then there was originally a hydrogen right there. So all of those hydrogens are there, right? And so all those carbons are happy with 4 bonds. All right, I just didn't draw them. But if you kind of just step back and think macroscopically what's happening, you are getting rid of all of the double bonds by adding hydrogen atoms, so everything's a single bond. So in this case, if we fully hydrogenated this molecule, we would actually have to add 2 moles of hydrogen gas, and it would all be single bonds like that. So you can prove it to yourself that these 2 molecules differ by 4 hydrogen atoms. Okay, and so the question is, can you explain the difference between hydrolysis and hydration? So look in the lecture notes for examples of that. Hydration is an addition reaction, so there has to be a double bond associated with it. Just like what we did here in hydrogenation, I could change this question and say, what's the the hydration product of this? So instead of adding 2 hydrogen atoms, I could add OH and a H to this molecule instead, because there's an alkene, a double bond that we're adding to, addition. Hydrolysis means that we're taking taking 1 molecule and splitting them into 2 smaller ones. So there's no double bond associated with that at all. So you're taking like 2 things and making it 1, that's condensation, or breaking it apart by adding water, that's hydrolysis. Okay, so let's keep going. All right, so 12, probably the hardest question in this one, because we are talking about hydration again, but this is like we did in class, a retrosynthesis. We are thinking about what is the starting material. What is the starting material for to get this product if we do hydration? So again, hydration is an addition reaction. So we need to start with an alkene, and we add water across the double bond in the form of hydrogen and OH. That's what we add across the double bond. So I even tell you that the starting material is a alkene, that you need to have a double bond there. But we can't just place the double bond anywhere. We need to be a little bit smart about this and think about it logically. Like in these reactions, we took the reactant, added OH and H across it to see what are the possible products, but now we're working backwards. We're working backwards. We know what the product is. What are we starting with? So we need to form a double bond. We just need to figure out where. So what I like to do is highlight the bonds, or in all of the hydrogens in the molecule, in the product, to figure out, okay, just do the opposite of a hydration. Remove a hydrogen and an OH group from the molecule and form a double bond instead, to figure out where that double bond can originate from. So the trick is here that there's actually 2 different places you can take hydrogens, because if we kind of go into this molecule and think about where are all the hydrogens at, there's a bunch. There's one there, there's one there, there's one there. So in a hydration reaction, you add the hydrogen and the OH in 2 carbons that are next to one another. So now the thought process is, well, where should we form the double bond? If we remove this OH and this hydrogen, we form a double bond right here. So if we redrew that, it would look like this. All right, and then you can ask yourself, you can redo the hydration and ask yourself, where could the OH be? The OH could go here, or it could go here. So we're ignoring Markovnikov additions right now, but that OH could go right here and be made if we did a hydration on this molecule. So that's one of the reactants that we can start with. So I'll just undo that. Well, ask yourself, where else could you remove an OH and a hydrogen where the 2 carbons are next to one another? So I'll note here, you won't be working with this hydrogen on that OH, because you can't take the hydrogen and the OH off the same carbon, because remember, we're forming a double bond between 2 carbons that are next to each other. So if we remove this OH and that hydrogen, then the double bond we form will be right here instead. So if we drew that product instead, so that bond remains single. So this is like the red path, all right? So a different path here. So the OH is gone, that hydrogen is gone, so the double bond would go right here. Sorry, that looks really bad. It would look like that. So these are the two reactants that could make that product. And then you can try it yourself. You can test it out yourself and see if you add a hydrogen and an oxygen to these molecules, could you get this product? All right. Okay. So there's 12 minutes left. Are there any specific question numbers you want me to go over, or any topics that you want me to go over? Question 8. Yeah. Okay. So question 8, if there's time, I'll do question 11. I thought I did 11. I already did 11. So we'll do 8. So in this reaction, we have a description of a chemical reaction occurring. So it will be helpful if you can recall chapter 2 naming. That will be very helpful to write out a reaction of what this looks like. So here we have a reaction of silver nitrate solution. So silver nitrate, so Ag, nitrate is a polyatomic, so NO3. So in my mind, I know that that is an ionic compound, that silver and nitrate are ions, and we're reacting it with copper metal, so just Cu neutral. Right. So in my mind, I know that this is a single displacement reaction because we have an ionic compound and a metal. But if you read on, you can definitely see that it is a single displacement reaction because it says the silver metal comes out of solution. So now we just have silver neutral, and then the solution turns blue because of the presence of copper 2+. So we have copper 2+, so an ion, and then nitrate is floating around as well. This doesn't have to be balanced. It doesn't matter to answer this question. So the first question is, what type of reaction is this? It's single displacement. Also, we can say that it's a redox reaction because the metals are changing its charge during the course of this reaction. And you can tell because the rest of the questions ask about what's being oxidized and what's being reduced. So the strategy here is to determine the charges of all of the metals. So the easy ones first are the neutral metals. Copper neutral, copper metal is neutral. Silver metal is neutral as well. But if we look at the other substances, they're actually ionic. Silver nitrate is ionic. So silver, this is Ag+, so that is a +1 charge. How is silver changing during the course of this reaction? It's going from a +1 charge to a 0 charge. So ask yourself, is that gaining electrons or losing electrons? It's gaining electrons because the charge is going down. The charge is reducing. So silver plus is being reduced. And so if you look at copper, copper is going from 0 to a +2 charge because it's a copper plus ion. Why isn't copper 2+ and nitrate not combined? It's not important in this question because we just want to know what copper, how is just copper changing. So here it really should be copper nitrate, but it doesn't actually have to be balanced for this this reaction because we I'm just describing it to you. So this should be Cu, NO3, 2 of them, but it doesn't really matter because we care about the copper charge, not the actual compound. So copper ion on the product side is copper 2+. So we see that this substance is losing electrons, so this is being oxidized. All right, and so we answered that question. What substance is being oxidized? It is copper solid, so make sure you're pointing to the reactant side. And then what substance is reduced? It's Ag+. And then the oxidizing agent, reducing agent. So here you kind of swap them. So the substance being reduced is the oxidizing agent. The substance being oxidized is the reducing agent. So this is copper, no, sorry, it is silver plus, again, pointing to the reactants. The reducing agent is copper solid. All right, so this one's a little bit more difficult because I am giving you a statement and I don't just give you like, you know, it'd be a lot more straightforward if I said something like Ag plus Cu gives Cu2 plus Ag. And then you can clearly see the charges of everything. If something was like this, you could be like, oh yeah, +1, 0, +2, 0, and you can see it very clearly how the charges are changing. But in this case, I'm telling you a description, and from that description, you should be able to deduce charges from chapter 2 or chapter 3 information that we talked about earlier this term. Okay. If you put Cu without the S, would that be incorrect? No, as long as what would be incorrect is if you put Cu2 plus. That's straight up wrong because that's a product. I just put S to differentiate that it's the neutral one, not copper 2 plus. So, and I can't really, this exam is multiple choice, so you'll know which one is the reactant, as long as you're aware of it. Okay, other questions? 6 minutes. Other questions in this packet? If not, then I might be done. If no one has questions. Seven. Okay. We did this in class. This is the same question from class. Read it. Which of the statements are true concerning an endergonic reaction? So endergonic implies a certain sign of delta G, Gibbs free energy. So delta G, we can have a positive or a negative delta G. So either energy of the reaction increases or decreases. Ender means positive, so delta G increases. So I like to just remember how the graph is. All right, so endergonic, your reactants are more stable, lower in energy than your products. So the axes here, that's energy. And this is like reaction progress. And so this is what an endergonic reaction would look like versus exergonic would look like that, where reactants are higher in energy than products. So if we look at all this, is the reaction spontaneous? It is not, because only negative delta G's exergonic reactions are spontaneous. So one is not correct. Energy must be provided to push the reaction forward. That's true, because the reactants are lower in energy than the products. You got to push it, give it energy. You have to push a ball up a hill in order to get it up the hill. So 2 is correct. The reaction is slow. So this is kind of a trick question, because when talking about energetics, it is not related to reaction kinetics at all. You can have spontaneous reactions, but they're really, really slow. So 3 is not correct, because delta G is not related to reaction kinetics at all. And then the last one is the reactants are more stable than the products. So if we look at this reaction, for an exergonic reaction, that is true. Reactants are more stable, they're lower in energy than the products, so it would be that one. And so, on your own, if we changed this to exergonic, go through the same things and see which ones would be correct. Yeah, so in an exergonic reaction, the product is more stable than the reactant. You tell me. So this is an exergonic reaction. This is reactants, that's products, the delta G is negative. Are the products more stable than the reactant? It is. Yes, it is. Okay. So I like to memorize the graph. The graph tells you a lot there. And so, in these reactants, I think we talked about this in class. If we had an exergonic and an endergonic reaction, which one has the larger activation energy? It's this one. The endergonic reaction, this entire curve up until here. So basically to get from here to here, that is the activation energy up to there, versus for an exergonic reaction, going from here to here, that is your activation energy. So it's a little bit smaller, or I guess a bit smaller for an exergonic reaction. All right. Okay. Other questions? No? Okay. So I will post the record. I'm going to stop recording. Yes, please. Can we be done? I'm really tired. Okay, stop recording.